Thank you very much. So I just wrote a few things on the board in order to recap what we have been discussing. So what yesterday we saw is that in the context of a general stratified group in the homogeneous sub-Laplacian L, there is this result of Krishna-Malcheri and Meda that shows that we can bound the convolution kernel of a function of the sub-Laplacian, so operator in the functional calculus of the sub-Laplacian, in terms of a Sobolev norm, the corresponding spectral multiplier, under the assumption that this function f is compactly supported, where what they obtain is that the order of smoothness you need to require on the function f is this something bigger, slightly bigger than half the homogeneous dimension of the group. And this homogeneous dimension is somehow a natural parameter that appears in the discussion of the geometry of this group. Is really the natural scaling dimensional parameter. In some sense, I mean, if you think of the proof how this result is obtained from Cauchy-Schwarz, starting from a weighted to estimate, given that the weight includes this homogeneous norm, so the distance from the origin with respect to the natural sub-Riemannian distance associated with the operator. I mean, if you compare this estimate with its Euclidean analog, and in particular this weight with the Euclidean analog of the weight, you see that in a sense, I mean, if you want to have to gain integrability by using this kind of weight and then thinking of applying Cauchy-Schwarz, of course, on the first layer, you gain exactly the same as you would gain with the standard Euclidean weight. But on the second layer, this weight contains the square root of the component of the second layer. So in a sense, if you want to gain the same as you were be gaining in the Euclidean situation, you have to pay twice the price in terms of derivative, and the third layer 3 times the price, and so on. And this somehow is one way of thinking of how then you get the homogeneous dimension instead of the topological dimension by doing this kind of discussion. Okay, and so we get that indeed, if you now want to investigate what is the minimal assumption of smoothness you want to put here, so what is the sharp threshold, for sure, Krishna-Malcheri and Meda prove that this cannot be bigger than half the homogeneous dimension. And this coincides in step 1, so in the Euclidean case with the topological dimension. And again, in the Euclidean case, there is a standard argument by using stationary phase, anyway, by analyzing some specific multipliers such as imaginary powers or other examples, let's show that indeed one cannot do better than the topological dimension. If you try to do the same on a stratified group, things are a bit more complicated. For sure, what you can get by a sort of perturbation argument freezing the coefficients is that you see a partial Laplacian in certain directions, so in the directions of the first layer. So for sure, you cannot go below half the dimension of the first layer, what I call the horizontal rank of this stretch. Okay, and so here we have a gap, and the problem is what is the actual threshold. And as I mentioned, even in the generality of a stratified group, it's not known for an arbitrary stratified group what this value should be. It is known in a few cases, and one of them is perhaps the simplest example, non-commutative example of the stratified group, so beyond RT, which is the Heisenberg group. And yesterday we started introducing a bit the notation. Here we have a many more explicit formula and tools that we can use to do this discussion. And we are seeing that actually in this case, this two-step group with first layer 2n dimensional, second layer 1 dimensional. So the homogeneous dimension is 2n plus 2, topological dimension 2n plus 1, and the horizontal rank is 2n. We have a quite explicit expression for the sub-Laplacian. So Laplacian in the first layer variable, sort of, sorry, here, that should be a derivative in the second layer variable, but with a weight, and then some sort of mixed term which includes this kind of angular derivatives in the x and y directions. And one interesting tool to use to analyze the sub-Laplacian is actually taking the partial Fourier transform in the u direction, because if you do that, then you get that the sub-Laplacian actually corresponds to a one-parameter family of operators, and mu is the dual variable to u, and this is given by this expression, which we call the twisted Laplacian on R2n. So the variables now are z or xy, And you get again, of course, the Laplacian in Z, this kind of potential term, quadratic with some scaling in mu, and then this other mixed term again. Okay? And by using the fact that one knows what is the actual, to say, spectral decomposition for this operator, one can study its spectrum, its eigenfunctions, and so on, it's possible to work out what the formula for the convolution kernel of a function of the sub-Laplacian is quite explicitly up to a Fourier transform in the center, so in the u variable, and this is given by this kind of expression involving the radial eigenfunction of the twisted Laplacian, that is this expression involving Laguerre functions. And as we have seen, by using the orthogonality properties of these Laguerre functions, one can actually get a very explicit expression for the L2 norm that shows that indeed, I mean, one can get the Plancherel formula that we discussed yesterday in more abstract terms. One can get it much concrete. And one observation that was done yesterday is the fact that if you look at this sum, this actually converges because this for fixed m, which is just a dimensional parameter, goes like n to the power of -2, and somehow there is some error here in the convergence, so it converges better than what you would need in principle, and so this is something that we will exploit in the next discussion. So what I'd like to show you is that actually in the case of the Heisenberg group, we can improve the L1 estimate obtained by Christian, Marcelli, and Meda, and push down the threshold to half the topological dimension. And I show you this argument, which I believe is the argument due to Hebbish, so I follow that argument to present this proof.
Oh,
yes.
You said that
Yes.
thinking about something different.
Yes.
If you consider this twisted Laplacian,
Yes.
you write a kernel.
Yes.
But this is a kernel with respect to the twisted convolution.
That's right.
That's right.
Yes.
So there are a lot of cancellations in the edge.
That's also true. Yes. 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 I mean, of course, I'm using this formula purely for two considerations, effectively. So, I mean, at the end of the day, all the cancellation disappear when you take the L2 norms. But yes, I won't use it more than just for them, to be honest. Yes. Okay. So let me just then try and work out what the idea is to get some improvement on the standard estimate. And the idea is that, as we have just seen, one tool comes from the decomposition that we have of the twisted Laplacian. So the fact that we can, if we wish, decompose the twisted Laplacian in two terms. Okay. One is what I call G mu, and the other one I call, say, A mu. Okay, this A is for angular because it has this kind of angular derivative, and G somehow is somehow related to the fact that this one is effectively a Grushin operator. This, at least if you look at it on the Heisenberg. Anyway, whatever the names we give to these parts. So we have that indeed the twisted Laplacian can be written as a operator G mu plus A mu, where G mu is nothing else than the rescale Hermite operator in R2N. So we have the Laplacian plus a potential. Okay? Whereas the other part has this kind of angular derivative terms in x and y. And what does it mean? It means in particular that if you apply this to a function f which is radial in z, then the derivative is just 0. And so this means the fact that this A mu term vanishes on radial functions, that actually the twisted Laplacian on radial functions has the same action as this harmonic oscillator when the function is radial. And so now, suppose now that we take a function f on the group, the Heisenberg group, so z and u variables, which is z radial. As we discussed yesterday, the kernels in the functional calculus for the sub-Laplacian are. Then, suppose that I want to consider the norm of, say, the square root of the twisted Laplacian applied to the partial Fourier transform in U of f. Now we think of it as a function in z. And this is L2 of R2n. Okay, so I just take the L2 norm in z. Well, I can just write this as an inner product. This L2 norm, then I bring all the terms L mu on one side, so I just get L mu, L mu, L mu. Okay. And then when I have that, I just observe that since I started with a z radial function, then actually the Fourier transform remains z radial. And so actually this applying the twisted Laplacian is the same as applying this harmonic oscillator. Okay? But now we have that the harmonic oscillator is the sum of two positive definite terms. So actually I can just throw away one of the two and keep the other. Okay. In physics terms is as we say that the total energy bounds the potential energy in some sense. Yes? And so when I do that, I can just rearrange things and rewrite this as mu over 4, mu square over 4. And then I have a weighted L2 norm on R2n of my function mu with this weight, model z, model the variable. Okay? So rearranging what gives us the fact that if we take this weighted L2 norm with mu on R2n, remember, then I bring things to the other side, I take the square root, so I have a constant 2. I take this mod of mu to the power -1. I have L mu to the 1/2 here, and then I have L mu. Okay? But now you see this equality is true with the same constant for any mu. And so the idea is that then, well, if you wish, you take the squares, you integrate in mu, you use Plancherel in the variable mu, and you recover an analogous inequality by taking Houdini and Plancherel, an analogous inequality on the group. So model Z, now we just take the function f and 2 of g, same kind of inequality. And now what comes instead of this mod of mu? Well, mod of mu is the Fourier transform of somehow the derivative, the central derivative. So remember that we discussed this also yesterday. We had this central derivative u, which we can make self-adjoint, to which this commutes with Laplacian, the sub-Laplacian, and so if you take the Fourier transform, that's what you get, and then you have the square root of the sub-Laplacian, and okay, so this is an inequality 2 of g, and then with some care, one can actually interpolate this inequality and obtain also a similar inequality where you can get fractional powers of the weight. Here we will get fractional powers of the corresponding operator for alpha is between 0 and 1. Okay, so that's the key idea. And now you see that we have a new weighted inequality, and which holds at least for radial functions f. And now let's try and apply it to the case that we're interested in. That is the case where this k, this small f, is actually a kernel associated with the functional calculus for the sub-Laplacian, because we know that these functions are radial in Z. So for convenience, let me introduce the notation at alpha lambda being just lambda to the alpha max f of lambda, so small multiplication of the original function. And then if I take this weight, power alpha, kernel f of L, this is a radial function. If I apply the previous inequality with this small f, I can obtain something like u to the minus alpha, Laplacian alpha halves, and then this of L. But now, since all these are operators acting on this convolution kernel, they are also part of the same functional calculus because they all commute. We can rewrite this actually as the kernel of another operator, which is just this. If I wish, I can put this power of L inside the L, and just put it. Okay? And so when I get this, then here I can effectively apply an analogous formula that I would have here, because effectively I work this out by just taking the partial Fourier transform, but because these two operators commute, one can see that this kind of eigenfunction decomposition works also simultaneously for the operator L and U. And so if I had a joint function of L and U, actually it's just modifying the formula here. And that's exactly the same formula that was even there. So if one believes in this whole modification of the previous formula, one can then apply the usual arguments of Laplacian and the orthogonality of the Laguerre functions to get that this expression is just the sum. But now I have an additional power of mu minus 2 alpha there. Then I have the f alpha with the eigenvalues. It's the Laplacian, and then I have the power of mu that comes from the Laguerre functions and orthogonality, the fraction of factorials that I had before, and then I can just redo the same scaling that we had before. So it's here, and I just sort of pull out the function, pull out the sum, I rescale, and then put the sum back. And what I get is that, well, I still copy the same expression, but then now when we scale this factor to n plus n, this power of mu has changed, and this makes it so that actually the factor that I get here also changes. So it's no longer mu n plus 1 that I had yesterday, but I also have to modify by this 2 alpha that came here. And so that's what it is. Then I have n plus 1 minus 2 alpha, lambda. So that's what one gets. And now one can observe that, well, before we had some error, and now we can use it because we can choose this alpha to be a little bit positive and still hope to get a converging sum. And this is now the term of the sum is essentially 1 plus n minus 2 plus 2 alpha. And so for fixed n, which is just a dimensional parameter, so this converges for alpha less than 1 alpha. And this is somehow exploiting the remaining error that goes in this summability, in this sum, for the summability of this sum. And effectively, this leads to bounding a weighted L2 norm with a partial weight just on the first layer variable of the convolution kernel, effectively with an expression which is an L2 norm of this F alpha. But if F was supported between -1, but between 1/2 and 2 as before, this L2 norm of F alpha is the same as the L2 norm of F. So by putting everything together, what we got is that we have this kind of inequality on the group. So the function f of L has variables Z and U, but we just get this weight in Z with an L2 norm of the multiplier for any alpha between 0 and 1/2. And this is an estimate which I believe has no clear sort of counterpart in the Euclidean setting, in the sense that here we get just the L2 norm of the multiplier, and here we get a weight, so some additional, some sort of integrability for free in the first layer that you don't pay in terms of any derivatives of the function. Okay, you just get this first layer weight for free, up to a certain power. And now what happens is that if you, for example, want to exploit this in order to improve the previous estimate, we go back to a more complicated estimate where we add also the weight, the full weight with the homogeneous norm. And you can ask for what sub exponents S this kind of estimate holds, still under the same support assumptions. Well, let's try and do this thinking of fixing the value alpha between 0 and 2, and we just do the diagram with beta and S, where does this estimate holds? Well, on the one side, because of the standard Crisp-Cherry-Meta estimate, the weighted L2 estimate, we can just, you see, this partial weight, we just can swallow it into the full weight, that is, this weight is bounded by the full weight to the power alpha plus beta, and therefore the estimate will certainly be true when S is bigger than alpha plus beta. So for sure, we will get this region by the standard Crisp-Cherry-Meta theorem. On the other hand, what we just proved is that when we don't have the full weight, but just a partial weight, when beta is equal to 0, then we just need no derivative. So also S equals 0. So this is the new estimate that we got. And then we can just interpolate again. And by interpolation, we get the remaining range, which means that this holds for any alpha between 0 and 1/2, and any S bigger than beta to 0. So somehow we get the same estimate as before with an additional weight for free. And this weight, which is just in the first layer direction, we don't pay in terms of derivatives. And this is what allows one, with this technique, to recover the missing integrability and somehow improve on the L1 estimate that we had before. Because now, if you think of doing Cauchy-Schwarz here, well, you need integrability in all variables in all directions. In the first layer, you have something for free, so you don't need to use the full weight for that. You still need to pay for the second layer weight double the price, but you don't need to pay for some part of the first layer weight. And that's why this kind of balance at the end gives us that by Cauchy-Schwarz, we recover exactly 1/2 derivative in the whole computation L1. And so we get this estimate for S bigger than, instead of 2n plus 2, that is what we had from the standard estimate, 2n plus 1. But this is the topological dimension in this case, it's just this gap that we have to fill. So this is the way that, I mean, was more or less how it is presented in this work by Hebisch, that observed that this can be obtained in the Heisenberg group, and similarly, independently, Müller and Stein with a slightly different approach, but contains also this kind of estimate, obtained independently the same result. And I guess at the time that was relatively surprising, because indeed, this topological dimension doesn't seem to have much to do with the underlying geometry, with the natural scaling parameter, dimensional parameter, and so on. But still, for this purpose of studying the integrability of the convolution kernel, so say Bochner-Ritz mobility on L1 or things like that associated with the sub-Laplacian, it's the topological dimensions of how the parameter that plays the role. And that is analogous to what you would have on MD, rather than the homogeneous dimension. Okay, so this holds on the Heisenberg group, but of course, the big problem is what about other situations, more general groups? I mean, we have this huge class of stratified group of any step, and as I mentioned, as of today, for arbitrary stratified group of step larger than 1, we don't know exactly what the sharp threshold is. Of course, after this work by Müller and Stein and Hebisch, a number of other studies have been sort of made on similar problems, and we actually know a number of results that is for a number of two-step stratified groups, not all, but at least certain class, so Heisenberg groups we mentioned, also Heisenberg type, so-called Métivier groups, or some variation of the Heisenberg groups, and even direct products thereof. One can definitely obtain this d/2 threshold, okay? And this is already in this paper by Müller-Stein, Efficiency, and Kiewicz. So these are all following this kind of first layer weighted Lacherel estimate approach. This approach has also been used in even beyond stratified groups, say complex spheres, or even quaternionic spheres. So there are works by Calvin-Shikora, Calvin-Kliman-Shikora, who sort of developed similar approach with the first layer weight. There are also results for Grushin operators using, again, this kind of approach. But then one notices that just by using this first layer weight approach, one cannot really treat the whole class of even two-step stratified groups. As a matter of fact, even when you go to direct product groups, so direct product of Heisenberg groups, you wouldn't so much get this kind of estimate, but an estimate with product weights. So Z1 plus Z1 to certain power, then 1 plus Z2 to another power, where these are just components of the first layer variable, the various factors. So somehow this shows that this kind of observation works in at least with the method that we have in a particular class of two-step groups, and the situation even for more general two-step groups is more complicated. In collaboration with Edward Müller, we managed to actually investigate the problem and obtain an alternative approach to this. And actually, we managed to obtain instead sort of a second layer weight approach, where we managed to, instead of getting this kind of estimate, obtain a different kind of estimate with 1 plus u here that works in another class of two-step stratified groups, where essentially there for the second layer weight we need to pay in terms of derivatives, but we pay the same price as in the Euclidean situation and not somehow double the price as it would come from the Christmas-Cherry beta approach. So there is a different approach, but that other approach is very, very much related also to special properties of the Laguerre function, because then if you start differentiating, putting a weight in mu, this means that you have to differentiate this kind of expression in mu, and a lot of identities with Laguerre function then become involved in all this kind of discussion. So it becomes technically complicated, and also one aspect that is a bit hidden because I haven't written the general formula here, but only for the Heisenberg group case, is that the Heisenberg group case has this kind of radiality embedded into it. And in particular here, we just see the mod of mu, that even when the second layer variable is higher dimension, like in Heisenberg type group, you still would get some sort of radiality in this second layer variable. But already when you work with direct products, you would start seeing sort of components of mu with separate indices and maybe a multi-index involved. And somehow, as the more complicated the two-step structure becomes, the more complicated the formula becomes. And it doesn't seem so feasible to actually use this kind of approach for even arbitrary two-step groups. I mean, it doesn't seem to lead to the result that one might at this point expect this after topological derivation. Okay, so one thing that we could prove, at least for two-step arbitrary two-step groups, and homogeneous sub-Laplacian thereof. This is a result of myself and Müller from 2016, is that the optimal threshold is never below d/2, but it's strictly less than q/2. So we know that at least for arbitrary two-step group, q/2 is never sharp, can always be better. And as I mentioned, we have a number of papers also other authors suggest that also show that actually there is equality in a certain number of cases, okay, even beyond Heisenberg. So, but for sure, q/2 doesn't seem to be the right answer, at least in this two-step situation, and most likely also in greater generalization. But as I said, I mean, this kind of approach seems to have some limitations very much related to this kind of special function identities and so on and so forth. And it seems to be a bit mysterious in a sense. I mean, we know that sometimes you get these better estimates, and that's good, but is there a more sort of underlying principle, sort of fundamental underlying principle that we can exploit here? And so one of the intuitions, I think, is also one of the things that which Detlef actually worked a lot and pushed towards is actually to try and connect this problem with the underlying geometry. And one way to do that is actually try to understand this problem from the point of view of estimates for the wave equation, because somehow studying the solution to the wave equation has a much more direct approach and much more direct connection with the underlying geometry. And so the hope is that instead of just dealing with all these very special formulas and get to the result, in some cases, one can better understand what is going on in this situation by looking, for example, at how the geodesic flow behaves in this context, and therefore maybe get some information on whether we can always expect this quality to hold, or instead if there might be some obstructions, also by looking more at the geometry. Okay, so now in the remaining time, I'd like to try to introduce this, and then tomorrow also go on with this idea of what is the relation of this problem with the wave equation. So the kind of wave equation estimates that I'm interested in are often known as Miyachi-Peral type estimates. And the idea is that I would like to bound some operator norm of the wave propagator, but I will put some spectral cutoff here. This chi1 we should think of as a cutoff, so a smooth cutoff between 0 and infinity, which is supported around 1. That's why I put this 1 there. Yes, and one may be interested in estimating this L1 operator norm, such an operator, and to show and to ask how it grows as a power of lambda. Okay, so this is the kind of estimate I'm interested in studying. And for lambda large, and you expect this to be true. Of course, if it's true for some alpha, I mean, true for larger alpha because lambda is large. So in a certain range of alpha with some infimum alpha naught, which would be the sharp, say, Miyachi-Peral wave threshold for the operator under consideration. Okay, and I call it Miyachi-Peral estimates because actually there is a work by Miyachi and Peral, actually two works, one by Miyachi, one by Peral, independent in the same year, from which one can deduce, among other things, that in the case of the Laplacian on RD, so the Euclidean case, then this estimate actually is true with this threshold being T minus 1 over 2. So after dimension, so but not after dimension, but dimension minus 1, so after dimension minus. Okay. So let me point out that from this estimate, one can deduce a number of consequences. Among other things, one can consider, again, this operator composed with a negative power of 1 plus the corresponding Laplacian or sub-Laplacian. And then effectively by doing a dyadic decomposition using this lambda to be dyadic parameters, it's not too difficult to see that from this estimate one can also deduce, in this case, a growth in the time parameter of this. Okay, I mean it's a bit, it's not too difficult, it requires a little bit of work, but let me point out that here I'm using an open range of alphas exactly because actually we need some epsilon in order to guarantee the summability. But since I'm just working with an open range, then the range actually remains the same. Anyway, and if one has this kind of estimate, let me just show you that this wave equation estimate actually implies a corresponding multipliers, meaning that if you take a function f from R to C which is even, then let me just rewrite this as f alpha on the root of L, 1 plus L minus half over 2, where f alpha here we just leave what you expect. So, and now I just subordinate this by using the Fourier transform to the wave equation. This I write the function as an inverse Fourier transform, it's Fourier transform, and since it's an even function, actually, I get the cosine transform, so I get the cosine term, which when you evaluate in square root of L, gives you exactly the wave propagator. Because of this kind of initial trick, I actually get the wave propagator already multiplied by this kind of power, inverse power of 1 plus the Laplacian, and therefore, here, I just get if I now take, say, the operator norm, I put the norm inside the integral, I will get something like alpha here. And then, if I know this kind of growth condition, I get this. And you see that now we have this kind of weighted L1 norm with the Fourier transform by Cauchy-Schwarz. We can bound it with a weighted L2 norm, which would be just the L2 norm, a Sobolev norm then of f alpha, when beta is at least alpha plus 1/2. If you do the Cauchy-Schwarz, you have to increase a bit the exponent in order to what you, so you multiply and divide by something that is integral. And so now if you assume as usual, we have something like the usual compact support condition, this is even, so maybe we have to ask something like that. The positive line the support is that, then you will just get that this is the same as the original. And so this kind of subordination argument shows that effectively the sharp threshold that we had in this L1 inequality can be bounded by the sharp wave threshold plus 1/2. And so you see that actually if you know this result on RD from that and this subordination argument, you recover the D over 2. So this 1/2 gap is not just a sort of a result of Cauchy-Schwarz, but actually it must be there because the other estimate is not improvable for the multiplier. Okay, and so actually this tells us that this knowledge of wave equation estimate may actually lead us to sharp results for the integrability and then one, so on. Okay, so interestingly enough, I mean, we know this result D over 2 for the Heisenberg group and the corresponding sub-Laplacian. So one can ask, what about the analogous wave equation estimate this time? And indeed, Müller and Stein in 1999 obtained the same result corresponding to the multiplier result on the Heisenberg. But let me point out that their method used, again, was very much based on this kind of very explicit expression that you can obtain from representation theory, from this kind of spectral decompositions. And as a matter of fact, this applies to the isotropic sub-Laplacian. That is the one that I wrote down. I didn't write the other ones, but you can imagine that, for example, in this sum of squares, you could just put some other coefficients in front of the xj and yj, maybe even coefficients which have irrational ratios or something like that. And then all this kind of formula will mess up. I mean, I don't have so much the symmetry, no longer radiality mu as you would have in the general situation. But still, I mean, the results, say, by Edish, and Kiewicz, and so on, are robust enough to give you the sharp Mittler-Mander result with D over 2. So they do not have problem with these non-isotropic Laplacians. Whereas the approach by Müller and Stein is very much related to this kind of a very explicit formula, this radiality. And as a matter of fact, there is a more recent work by Müller and Zeger who extend again this kind of sharp Miyachi-Perard result for the wave equation to Heisenberg type groups, but again for the isotropic sub-Laplacian of the Heisenberg type group. So effectively are those for which again you have this kind of radiality in mu, and their techniques do not seem to be suitable to actually attack also the more general situation. Whereas for the multiplier problem, we know that it's possible to always have to go to in that set. And so actually what we did recently with Detlef is to develop an alternative approach to study the wave equation estimate, which is more related to the underlying geometry, the irregularity of the underlying geodesic flow, which actually allows one also to tackle the similar problem, but for example, on arbitrary either non-isotropic sub-Laplacian on Heisenberg group form, and actually applies to arbitrary sub-Laplacian on Métivier groups. Okay, so we now know that the same result holds true for the wave equation with b minus 1 over 2, also for Métivier groups. So somehow we get a result that would correspond to this result by say efficiency in Kiewicz on general Métivier groups. Okay, but for the wave equation. And somehow, apart from the fact that we get a result, which in a sense, by comparison with the multiplier result might have been expected in some sense, I think it's really the method which is a bit more interesting, because the hope is that actually this method may be actually generalized with wider classes and of groups and sub-Laplacian, and especially because it's very much related to the underlying geometry and to the geodesic. So let me just try to give you some ideas, at least, of some basic heuristics about studying this estimate for the wave equation. So, well, remember that by left invariance and homogeneity, L1 operator norm of this kind can be reduced to the L1 norm of the corresponding convolution kernel, and actually, but you can also, I mean, here I put just a time parameter. I assume this to hold for all times, but actually, in the say in any situation where you have homogeneity, this is kind of for free. This time independence, and so you can just put time equals 1, at least in this situation of homogeneous sub-Laplacian, and so you are reduced to proving something like with the evolution kernel of this kind of estimate. Okay, and well, what we know here, we know that by Ivanitsky's theorem, actually this function, so I apply this operator to the delta n0. This is just an alternative notation for the convolution kernel, this operator, just to clarify. This function is actually a Schwarz class function because this chi1 is smooth and complex supported with Schwarz, and it is actually a Schwarz function at scale 1 over lambda, because you are just dilating the same function with a set parameter, and so if you look at this space,
G1, this function G1, it could be 1 at 0, yes?
No. I want it to support around 1, but 0 at 0. Yes. In a neighborhood of 0, it's just 0. Yes.
In a okay.
Yes. Okay, 1 is
Okay.
Okay, so only one here. Thank you. And not only that, but by scaling considerations, we can also see that sorry, P norm or any P is just an appropriate power of the parameter lambda scale. And so now, if you want to study the one norm, this guy, and apply the wave propagator, well, at least heuristically, you can think that this thing is supported in a ball of radius about 1/λ up to some Schwarz space. Okay? So this is the initial support of this kernel. And then you apply the wave propagator. But then you have the finite propagation speed property for the wave equation, which tells you that you cannot go beyond distance 1, because here we're starting time 1 of the initial support. So again, by arguing a bit carefully with this Schwarz space, you can ignore the Schwarz space and show that actually, if this is the ball of radius 1, you're not going beyond something which is like 1 plus 1/λ. But of course, if lambda is large, this is again essentially 1. So everything up to Schwarz space lives in a fixed compact set. And now if you believe that this is true, you can apply Cauchy-Schwarz to bound the one norm with the L2 norm and just get the same thing, but with the L2 norm. And now here, the cosine family just bounded on L2, because here is a bounded function, precipitation damage in the wave equation. And now, for this guy, we do know the L2 norm. So that's what it is. And so you see that if, as soon as you believe this to be supported in the fixed radius, at least you get this bound, which of course is not what you'd like to get, but at least we start getting some. And at least in the Euclidean case, this is almost the right amount, because you would want to see b minus 1/2. In the Euclidean case, you just get Dirac. And so the point is that in the Euclidean case, what happens is that actually the singular support of the wave propagator is here. And so when you apply the wave propagator, effectively, you shouldn't think of the result just being supported in this full ball, but only around the singular support, with maybe with an annulus of thickness 1/λ. And then, if you do that, in the Cauchy-Schwarz, you actually gain a lambda to -1/2, which then gives you the right amount there. So at least this geometric kind of picture shows you that this might lead you to the right heuristics, but you need to use something more sophisticated than just finite propagation speed. You need also to be able to justify why this is possible. Okay, but why this concentration is around the singular support, and this is somehow what requires actually, and this is what one does, to use a more sophisticated approach by representing the cosine families of the wave propagator in terms of Fourier integral operators, to which one can apply more sophisticated methods. For the analysis of singular integrals, that indeed allows one to identify this kind of singular support and have better bounds. Okay, so let me just point out that, of course, this argument also shows that in the case of non-elliptic operators, such as the sub-Laplacian higher steps, stratified groups, then these heuristics actually is not really the right one. I mean, things are even more complicated. because just by this argument you get this Q over 2, which effectively would be the same as a kind of simplified proof of just plugging these multipliers into the Christmas-Ceremera estimate, you effectively would get this lambda Q over 2. This is more geometric, the more geometric way to see why this estimate, at least for this multiplier, should be true. But then you are missing much more than that. And so this somehow, at least to me, explains why you cannot just expect to be able to apply exactly the same argument as in the RD case as what you would to get the same result in this case.
Just a quick question, if you apply directly, because this is a multiplier. Right?
Yeah.
And if you, so it should satisfy some kind of nibbling or.
Well, I mean, if you use the version for compactly supported one, because this is compactly supported.
Yes, this is compactly supported.
Yes, so.
By you dilate.
Yes, then you may have to redilate, since it's a one norm, and you can rescale it. So then
only one part, not the second part, because you don't dilate cosine.
Yeah, but then you dilate everything, so you just put the lambda there. And then effectively, when you do that, then the support is fixed. And then you just pick up powers of lambda when you do derivatives, and you pick up exactly Q over 2 power.
And exactly you get the same.
Yeah. So this is a sort of a very geometric way to show why you can expect this estimate, but it's also telling you that here we are losing a lot in the case of the sub-Laplacian operators. And yeah, so let me just mention the fact that, and I try to tell you something more tomorrow about this, that this kind of approach can be justified for the Laplacian or more general elliptic operators actually by having a Fourier representation for the corresponding wave propagator. And here, underlying this representation, as I said, I mean, there is this finite propagation speed property. So this idea that actually waves propagate along geodesics, which in the case of RD are just a straight line emanating from their original point, so that's why you get this kind of spheres and the similar supports. But in general, for more general manifolds and more general geometry, you might get some pictures which are, at least for large times, very complicated. But in the at least for elliptic operators, the underlying geometry is a Riemannian geometry, and therefore, at least at small scales, you would still see a picture maybe with curve, but of a similar kind. So it might not be so completely unexpected that at least locally for small times one can recover similar kind of results. And indeed, at least on compact manifolds, for elliptic operators, one can get essentially for this N1 bounds the same results as one can get on RD. But the geometry in the case of stratified groups or more general sub-Riemannian manifold is more complicated also in terms of the geodesic flow and the geodesic structure. So maybe now we can try and show this picture just to clarify why you cannot expect even for small scales to get this kind of nice propagation just from a single point. Yes. Okay, this was just to show a picture that hopefully clarifies a bit what is going on. Again, this is related to the Heisenberg group situation. Here, as I mentioned to you, the idea is that when we want to talk about lengths of curves, we need to speak of admissible curves or horizontal curves. That is, when we speak of, for example, the Heisenberg group, we have a fixed set of first layer direction, which are given by these vector fields xj and yj. This is a 3D Heisenberg group, so m is equal to 1, you only have two direction x and y. This just span a 2D plane. At the origin, these two vector fields are just d over dx, d over dy, or x1 and x2 in that graph. So indeed, if you freeze the coefficient at the origin, just take a partial Laplacian in the x1 and x2 directions. But when you sort of move from the origin, then this plane that is spanned by x1 and x2, so x and y, in this notation, tilts. And so the idea is that you should be able to join any point with any other point of the Heisenberg group by horizontal curves, that is curves which are tangent at every point of this kind of distribution of planes. And you see, actually, it's possible in the sense that even if, when you are, say, at the origin, you cannot go up directly in the u direction, you can just leave the origin perhaps in the x1 direction there, then the plane tilts, and you can start going a bit up, and then the plane tilts again, you can start sort of spiraling, and by this kind of spiraling movement, you can also move up in this forbidden direction. And then when one has these admissible curves, indeed, one can speak of geodesic in the sense of length minimizing curves. And one can actually set up a system of geodesic equations, which can be dealt with, somehow set up by setting up a system of Hamilton equations in an appropriate Hamiltonian in the cotangent space, and then projecting everything onto the manifold. And this kind of cotangent representation allows us to speak of this sub-Riemannian exponential map, whereby you fix the starting point in initial covector, and then you get a corresponding geodesic with that initial covector. And as it happens, well, you can take this initial covector somehow horizontal there, and you just get this geodesic, which at every point is tangent to this distribution of planes. But if you start with the different initial covector, the geodesic may have the same initial vector. This is different from the Riemannian situation where the initial vector determines the geodesic. It's not true in the sub-Riemannian setting. And you see, the more this initial covector tilts and becomes more and more vertical, then you see this kind of geodesics that become more and more spiraling. And all of these are locally length minimizing curves for the sub-Riemannian geometry, but they stop being globally length minimizing. Now, if you join all the endpoints of these geodesics of length 1, you get what you could think of as sort of a unit sphere, at least in RD, what you would get by taking straight lines of length 1 from the origin. You just get the sphere, and you get some sort of geodesic sphere or wavefront for this situation. And what you get is actually a surface of revolution, which looks like that. So, as at least in the neighborhood of the sort of equatorial region, if you wish, it's much more regular, looking more like a standard sphere, but around the u-axis, this forbidden direction, you have these infinitely many zigzags. So it's a much more complicated structure. And also, as I mentioned, you can imagine that if you just take the whole dilates going towards the origin in order to get the actual geodesic ball, well, you see that all the zigzags are actually inside of the ball. So this means that a lot of these geodesics stopped being length minimizing, because you could get a better geodesic or shorter length getting to the same point. It's inside of it. So this is to tell you that even locally, the geometry is much more complicated than in the Euclidean or Riemannian one. And so one can actually expect to get a much harder somehow life if you want really to get a precise understanding of what is going on there, especially if you expect to get this d minus 1 over 2 exponent there. So, but trying to tell you then tomorrow is a bit some ideas on how we try to approach this problem, at least in the case of the Heisenberg group, and develop a method which is more related to the underlying geometric structure to better understand this problem of L1 estimate with the regulation. Okay.
Thank you very much, Alessio, for a very interesting talk. Are there any questions? That's it.
I have a question to your first part, because when you started to use the wave equation, so only second order operators can be.
Yes, that's right. Yes.
But again, question about your theorem with that you may always go below a little bit.
Yes,
below, at least a little bit below.
That's right.
Half of the homogeneous dimension.
That's right.
What about if you consider not second order differential operator, like Copeland operator we talked about yesterday?
Yes. So that approach does not apply as it is written. I mean, pretty much convinced it should be true. The proof that we have for that is specific to second order. So effectively, as I mentioned to you, I mean, there is this very nice approach developed by Ebisch and Sienkiewicz that applies to Rockland operator on Heisenberg and even Métivier groups, which somehow allows one to avoid all this kind of explicit function expansion. You don't even need to see any of that, but still behind the scenes, there is still some sort of sub-elliptic estimate that allows you to sort of bound the total energy from below by the potential energy. So that part can be made sense of even in higher order, some way or another, but then you can avoid all this special function machinery and still get the same result. So their approach actually tells us that there are a number of examples, even in higher step, and they write this in the paper, where you can go below half the homogeneous dimension. So it's known that it's possible in a number of examples, even in higher step, even on Philip light.
But your theory with that is for
two-step and sub-Laplacians. And because our approach instead, in order to be able to apply that to all two-step groups and not just to some classes, we wanted to use the second layer weighted estimate, not the first layer weighted estimate, and for that, at least at the moment, our machinery is very much based on somehow having a more precise knowledge of the eigenfunction expansion. So it's not true that we strictly need to have those. I mean, we showed, for example, this is a different work, but with Gianmaria Dallara, that actually for Grushin operators, we can now show this positive result with half the topological dimension on R2. For Grushin operators, with some mild assumptions on the potential. I mean, if you put x squared, you get Hermite, and you get again a sort of Hermite function, which are relative to the Laguerre function moving to a similar machinery. But we could do this for arbitrary, say, single well potentials with some mild assumptions. Not only polynomial, not something comparable to a polynomial from above and below, but even more general than that. I mean, we have some mild assumption that polynomial single well, but most polynomial anyway, that allows one to get this improvement without a topological dimension. And this uses the second layer technique. So what I mean is that we know that this second layer approach can be made to work even without this Laguerre function specifically. One can, or a Hermite in the case of Grushin, one can do this even in greater generality, but becomes technically very, very, very demanding in a sense. And so, in a sense, the hope would be that a more geometric approach, again, maybe based on the wave equation in a different way, could help actually understanding this problem without really having to go studying function expansions, without really being able to rely on special function estimates or.
Any other questions? If not, then thank you very much, Alessio, for a nice talk. And we will start at 11:30. A little question about the dinner tonight. Could you raise your hands? Anybody who is interested in attending dinner?